The National Electrical Code, or NEC, does not explicitly require individual power calculations for all in-one residential services. However, some local jurisdictions have adopted their own interpretations of the NEC or implemented additional requirements. The Canadian Electrical Code, or CEC, requires calculations for each panel feeder in addition to the whole dwelling calculation. CEC Table 24 states that the demand factors for individual panel feeders are different from those for the entire dwelling. Practices may vary depending on the specific jurisdiction. In some areas, individual panel calculations may be required, while in others, only a dwelling calculation may suffice. To ensure compliance with applicable codes and regulations, and to avoid potential delays or conflicts with plan reviewers, it is recommended to follow these best practices. Firstly, check with local authorities. Consult with the local building or electrical department to determine their specific requirements. Secondly, perform individual panel calculations. If required by the jurisdiction, perform calculations for each individual panel feeder to ensure it meets the applicable demand factors. Thirdly, consider a larger service. If the calculations indicate that the total load cannot be distributed to the individual panels within the 200 amps limit, consider increasing the service size to a higher amperage, for example 450 amps. Fourthly, use appropriate equipment. Ensure that the equipment used, such as breakers and wire, is rated for the appropriate amperage. Fifthly, document calculations. Keep records of all calculations performed for future reference and inspection purposes. Explain the reasoning behind the additional calculations to the contractors. Provide them with information about the relevant codes or regulations. Discuss the potential consequences of not meeting the requirements, such as code violations or safety issues. Offer suggestions for how to reduce the load or increase the service size if necessary. When performing electrical calculations for a residential dwelling with a 400 amp service, understanding the nuances of the National Electrical Code, or NEC, and local jurisdictional requirements is crucial. A common setup involves an all-in-one service that includes an internal 200 amps 40 space panel, along with a 200 amps 2-pole breaker feeding a remote panel. The standard approach for calculating such a service typically involves conducting a dwelling calculation as per NEC section 220.30, along with providing panel schedules. However, it doesn't always necessitate performing individual calculations for each panel. This approach can sometimes lead to discrepancies, particularly when local plan reviewers demand complete calculations for each panel feeder in addition to the overall dwelling calculation. The challenge arises because the demand factors used for an entire dwelling calculation differ from those applicable to individual panels. Consequently, situations can occur where the total dwelling calculation yields a demand of, say, 300 amps, yet distributing the loads and calculating the individual panels to remain under 200 amps each becomes problematic. This situation often results in increased equipment costs for installations involving a 400 amp service, especially when only mains are considered. To navigate these complexities, it's essential to understand the best practices and considerations for ensuring code compliance while managing costs effectively. Firstly, it is important to understand the role of the National Electrical Code, or NEC, in electrical installations. The NEC serves as a comprehensive guideline for safe electrical practices, but its adoption and enforcement can vary significantly among different jurisdictions. Some local authorities may have amendments or interpretations that go beyond the NEC baseline requirements. Therefore, consulting with local building or electrical departments is crucial to ascertain specific requirements for electrical installations in the area. This consultation can help clarify whether individual panel calculations are mandated in addition to the overall dwelling calculation. When performing electrical calculations, the general approach involves determining the total connected load and applying appropriate demand factors to estimate the maximum demand. The NEC provides guidelines for calculating branch circuit, feeder, and service loads. Article 220 of the NEC outlines the requirements for calculating these loads in residential, commercial, and industrial settings. For residential dwellings, NEC Section 220.30 provides a simplified method for calculating the service load, which takes into account the dwelling square footage, appliance circuits, and other loads. This method often results in a lower demand than the sum of all individual loads due to the application of demand factors. However, local jurisdictions may require a more detailed calculation that considers the specific loads on each panel. In cases where individual panel calculations are required, it's essential to account for the demand factors applicable to each panel's loads. These demand factors may differ from those used in the overall dwelling calculation, reflecting the diversity and usage patterns of the loads connected to each panel. For example, lighting loads, receptacle circuits, and appliance circuits may have different demand factors depending on their specific applications. Furthermore, it's crucial to consider the non-coincident loads, which are loads that are unlikely to operate simultaneously. These loads can be assessed separately and included in the calculation based on their individual demand factors. When distributing the loads across multiple panels, careful planning is necessary to ensure that each panel's calculated load remains within its rated capacity. This planning involves strategically assigning circuits to different panels to balance the load and minimize the likelihood of overloading any single panel. In situations where the calculated load exceeds the panel's capacity, several options can be considered. Firstly, reducing the connected load by using energy-efficient appliances or implementing load management strategies can help lower the overall demand. Secondly, increasing the panel's capacity by installing a larger panel or adding additional panels can provide more headroom for the connected loads. Thirdly, adjusting the distribution of loads among the panels to better balance the demand and prevent overloading can optimize the system's performance. When faced with challenges in meeting the load requirements within the existing service capacity, consider exploring alternative service configurations. One option is to upgrade the service size to a higher amperage, such as 450 amps, to accommodate the increased demand. This upgrade may involve replacing the service entrance conductors, overcurrent protection devices, and other components to handle the higher current. Another approach is to implement a load management system that monitors and controls the electrical loads to prevent exceeding the service capacity. These systems can prioritize essential loads and shed non-essential loads during peak demand periods. Additionally, consider using energy storage systems such as batteries to supplement the grid supply during periods of high demand. These systems can store energy during off-peak hours and release it during peak hours, reducing the strain on the grid and lowering energy costs. When addressing contractor concerns regarding the additional calculations and potential cost increases, effective communication and education are essential. Explain the reasoning behind the more stringent requirements and the importance of ensuring code compliance for safety and reliability. Provide contractors with clear and concise information about the relevant codes and regulations, as well as practical guidance on performing the necessary calculations. Offer suggestions for optimizing the electrical design to reduce costs without compromising performance or safety. For example, using energy-efficient lighting and appliances, optimizing circuit layouts, and implementing load management strategies can help minimize the overall demand and reduce the required service capacity. Additionally, explore opportunities for value engineering, which involves identifying cost-effective alternatives that meet the project's objectives without sacrificing quality or functionality. In conclusion, electrical calculations for residential services require a thorough understanding of the NEC, local jurisdictional requirements, and best practices for load management and distribution. Consulting with local authorities, performing accurate panel calculations, and implementing appropriate load management strategies are essential steps for ensuring code compliance, safety, and cost-effectiveness. By addressing contractor concerns and providing clear guidance, electrical engineers and designers can facilitate the successful completion of residential electrical projects while meeting the needs of all stakeholders. The process begins with a comprehensive assessment of the dwelling's electrical needs. This assessment involves identifying all connected loads, including lighting, appliances, heating, ventilation, and air conditioning or HVAC systems, and any other electrical equipment. Each load's voltage, amperage, and power factor should be determined to accurately calculate its contribution to the overall demand. Once the loads have been identified, the next step is to calculate the total connected load. This calculation involves summing the power consumption of all individual loads, taking into account their respective duty cycles and operating characteristics. The total connected load represents the maximum potential demand if all loads were to operate simultaneously at their rated capacity. However, in most residential settings, it is unlikely that all loads will operate simultaneously. Therefore, demand factors are applied to the connected load to estimate the maximum demand that is likely to occur under normal operating conditions. Demand factors are based on statistical data and empirical observations of typical load patterns in residential dwellings. The NEC provides demand factors for various types of loads, taking into account factors such as the size of the dwelling, the number of occupants, and the types of appliances and equipment installed. These demand factors are typically expressed as a percentage of the connected load, with lower percentages applied to loads that are less likely to operate simultaneously. After applying the demand factors, the resulting value represents the maximum demand, which is the estimated load that the electrical service must be capable of supplying. This value is used to determine the appropriate size of the service entrance conductors, overcurrent protection devices, and other components of the electrical system. In addition to calculating the service load, it is also necessary to perform calculations for individual panel feeders. These calculations are essential for ensuring that each panel is adequately sized to accommodate the loads connected to it and that the conductors and overcurrent protection devices are properly rated. The NEC provides guidelines for calculating feeder loads, taking into account the specific characteristics of the load served by each feeder. These characteristics may include the type of load, its duty cycle, and its power factor. When calculating feeder loads, it is important to consider the diversity of the loads connected to the feeder. Diversity refers to the degree to which the loads operate independently of each other. Feeders that serve a diverse mix of loads, such as lighting, receptacles, and appliances, typically have lower demand factors than feeders that serve a more concentrated set of loads, such as a dedicated appliance circuit. The NEC provides demand factors for various types of feeder loads based on their diversity and operating characteristics. These demand factors can be used to estimate the maximum demand on each feeder and to select the appropriate size of conductors and overcurrent protection devices. In some cases, it may be necessary to perform load studies to determine the actual demand on individual feeders. Load studies involve monitoring the current and voltage on a feeder over a period of time to measure its actual load profile. This data can be used to refine the demand factors and to ensure that the feeder is adequately sized for its intended use. The data can then be used to determine the maximum demand on the feeder and to compare it to the calculated demand. If the measured demand is significantly higher than the calculated demand, it may be necessary to increase the size of the feeder conductors or overcurrent protection devices. Once the service and feeder calculations have been completed, the next step is to select the appropriate size of conductors and overcurrent protection devices. The NEC provides tables and guidelines for determining the ampacity of conductors, based on their material, size, insulation type, and installation method. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. The overcurrent protection devices, such as circuit breakers and fuses, must be sized to protect the conductors from overload and short-circuit conditions. The NEC specifies the maximum allowable overcurrent protection for various types of conductors based on their ampacity. In addition to selecting the appropriate size of conductors and overcurrent protection devices, it is also important to ensure that all electrical equipment is properly grounded and bonded. Grounding provides a low impedance path for fault current to return to the source, which helps to protect against electrical shock hazards. Bonding ensures that all metal parts of the electrical system are electrically connected, which helps to prevent voltage differences that could create shock hazards. The NEC provides detailed requirements for grounding and bonding, including the size and type of grounding conductors, the methods of connecting grounding conductors, and the requirements for bonding metal enclosures and equipment. Adhering to these requirements is essential for ensuring the safety of the electrical system and protecting against electrical hazards. Another crucial aspect of electrical installations is compliance with arc fault circuit interrupter, or FSI, and ground fault circuit interrupter, or GFCI, protection requirements. FSIs are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. GFCIs are designed to detect ground faults, which are electrical conditions that can cause electrical shock hazards. The NEC requires FSIs and GFCIs in certain areas of residential dwellings, such as bedrooms, living rooms, and bathrooms, to protect against these electrical hazards. FSIs and GFCIs work by monitoring the current flowing through a circuit and detecting any abnormal conditions that could indicate an arc fault or ground fault. When an arc fault or ground fault is detected, the FSI or GFCI trips the circuit, interrupting the flow of current and preventing a fire or electrical shock. It is important to ensure that FSIs and GFCIs are properly installed and tested to ensure that they are functioning correctly. Regular testing can help identify any potential problems and ensure that the devices are providing the intended level of protection. In addition to compliance with the NEC, it is also important to consider energy efficiency when designing and installing electrical systems. Energy-efficient lighting appliances and HVAC systems can significantly reduce energy consumption and lower utility bills. The use of LED lighting, Energy Star certified appliances, and high-efficiency HVAC systems can help to minimize the energy footprint of a residential dwelling. Furthermore, the installation of smart thermostats and energy management systems can help to optimize energy usage and reduce waste. These systems can monitor and control the temperature in different areas of the dwelling, adjust lighting levels based on occupancy, and automatically turn off appliances and equipment when they are not in use. By implementing energy-efficient design strategies and technologies, it is possible to create a more sustainable and cost-effective electrical system. When addressing the concerns of contractors regarding the additional calculations and potential cost increases, it is important to communicate the benefits of these measures. Explain that proper electrical calculations and code compliance can help to ensure the safety and reliability of the electrical system, prevent costly repairs, and protect against electrical hazards. Emphasize that energy efficiency measures can lower utility bills and reduce the environmental impact of the dwelling. Furthermore, provide contractors with the necessary training and resources to perform the required calculations and install the necessary equipment. Offer assistance with code interpretation and compliance, and provide access to technical support and educational materials. By working collaboratively with contractors and providing them with the tools and knowledge they need, it is possible to ensure that residential electrical projects are completed safely, efficiently, and in compliance with all applicable codes and standards. Remember that electrical codes and regulations are in place to protect lives and property. Compliance with these codes is not only a legal requirement, but also a moral obligation. By adhering to the NEC, local jurisdictional requirements, and best practices for electrical design and installation, electrical engineers and contractors can help to create safer, more reliable, and more energy-efficient residential dwellings.